Welcome to the problem solving session on topic traveling salesman problem. Actually, I wanted to conduct this session live because that would have given you a better insight into the steps uh, for solving this type of problem. Anyway, it doesn't matter. You can still solve the problem by pausing the videos at several points where I tell you to do so. Okay. So anyway, let's begin. Traveling salesman problem is a class of problem that finds application in many fields. Here, we are going to consider its special application that involves a salesperson who wants to complete a tour by visiting several cities. And in doing so, the salesperson wants to ensure that the tour is completed by covering minimum distance or in minimum time and consequently minimum cost. Here is an example of 5 cities, and the salesperson wants to complete a tour of 5 cities. That means the salesperson must travel to every city in this tour. Okay, so let's consider one of the several possible ways of completing this tour of 5 cities. Let's say that the salesman starts his journey from city 1. He goes to city 2 first. From city 2 he goes to city 3. From city 3 he goes to city 5. From city 5 he goes to city 4. From city 4 he goes to city 1 and completes his tour or journey at a point where he had begun his tour. Okay. In traveling salesman problem, we assume that every city is connected to every other city. Okay. So if I want to draw a network showing that every city is connected to every other city, it would look like this. So city 1 is connected to city 3, is connected to city 2, city 5 and city 4. City 4 is also connected to city 1, 3, 2 and 5. City 5 is also connected to city 4, 1, 3 and 2. City 2 is also connected to every other city. So that is the picture showing that every city is connected to every other city. Okay, so this is the assumption in traveling salesman problem. And this is also known as Hamiltonian network, which means that the salesman completes a tour without having to travel any city twice. Okay, so anyway, we'll not discuss this. So, and the constraint is that the salesperson should travel every city in the tour exactly once. Okay, so let us introduce a variable xij, and xij is a binary variable that can hold only two values, 1 and 0. So xij is 1 if city j is reached from city I and is 0 if that is not the case. Okay, the meaning of this is that if you pick any particular city, let's say for example we pick city 4, and then we consider all the possible ways of approaching this city, then those ways are like this. I can approach city 4 from city 1. I can approach city 4 from city 3. City 4 can also be approached from city 2 and can also be approached from city 5. Okay, so this thing is left out. In general, if there are n cities, then there are n minus 1 factorial ways, possible ways of completing the tour of n cities. Okay, so if we consider all these possible ways of completing the tour involving n cities, then there is a tour where the salesperson approaches city 4 from city 1. There is some other tour in all the possible ways where a salesperson approaches city 4 from city 3, there is still other combination, or there is still other way in which the salesperson might approach city 4 from city 2, and in still some other way the salesman approaches city 4 from city 5. Okay, so if I write for city 4 x x I j, so x, we are reaching city 4, hence j is 4, and x14, that means city 4 is approached from city 1. Similarly, x24, x34, and so on up to x54. Okay, so out of these 5 variables, only one will be 1. Okay, so which means that if in a particular possible way of a tour, if the salesman approaches city 4 from city 2, then only x24 will be 1 and the remaining will be 0. Okay, in some other tour, it might be possible that the salesperson approaches city 4 from city 3. In that case, x34 will be 1 and x24 will be 0. Okay, so this is the meaning of xij. So let me clean it up. Okay, so this is the mathematical model. What we want to minimize here is the product of Cij into Xij. Cij is the cost incurred for traveling from city I to city j, and the cost will be incurred only if this only if city j is reached from city I, just like the definition of Xij. Okay, so as we are considering all the possible combinations, the subscripts are generalized to ij. Okay, so uh, let me introduce this summation to you, the inner summation and outer summation. So there are two summations here. So first of all, this inner summation, if I expand the inner summation, then the problem statement or the objective function look like this: summation of I equals to 1 to n, that's the outer summation, and the inner summation when expanded, C I 1 x I 1 at j is 1 plus C I 2 into x I 2, j is 2, j is 3, C I 3 into x I 3 plus and so on, plus C I n into x I n. Okay, so that is the expansion of this inner summation. Okay, and then if you expand the outer summation, then we will substitute the values of I. So C1 1 into x 1 1 plus C1 2 into x1 2 and so on up to C1 sorry C n n into x n n. Okay, so this is how this objective function expands to. Okay, so let me erase this. Okay, and this objective function is subjected to following constraints. This is subjected to, first constraints is summation I equal to 1 to n of xij equals to 1, and this summation has to be repeated for every j. Okay, for j from 1 to n. So I will explain you how to expand this constraint. And then here's the second constraint: summation j equals to 1 to n of xij equals to 1 for all the i's. Okay, so let's understand what these constraints mean. Okay, so let me expand this summation first. The summation expands to, as we have a summation going from I equals to 1 to n, so x1 j, so I'm not keeping the value of j, I'm simply keeping the value of I. So x1 I equals to 1 plus x2 j plus x3j plus and so on up to plus xn j. Okay, then this equation has to be repeated for every j. Okay, so this equation for j equals to 1 becomes x11 plus x21 plus and so on up to plus xn1 equals to 1. Okay, so that is the equation wherein j equals to 1. Similarly, for j equals to 2, we get another equation saying x12 plus x22 plus and so on up to plus x and 2 equals to 1. And I have to continue this till j equals to n. Okay, then I can continue writing equations. Okay, so what is the meaning of this? x11 plus x21 plus and so on to plus xn1 equals to 1. This means that this summation must be equals to 1. That means out of these terms only one can be equals to 1 and others should be 0. Okay, let's say if x21 is 1, which means that the salesperson approaches CT1 from CT2 and every other term in this equation is 0. x11 is 0, x31 is 0, x41 is 0, and finally xn1 is 0. That means CT1 is approached only from CT2. Okay, there is no other city from which the CT1 is approached. So this is the meaning of this constraint. Similarly, let's talk about the second constraint, and let's say that in this constraint uh, x12 is 1 and every other term here is 0, which means that the CT2 is approached from CT1 only. Okay, that means CT2 is not approached from any other city except CT1. Okay, so this is the meaning of this constraint, that any city can be approached can from only one other city. So this is the meaning of the first constraint. Similarly, let's look at the second constraint. Let's clean it up. Similarly, the second constraint meaning is like this. So I will expand here itself. If I expand the summation, we have x I 1 as value of j is 1, xi1 plus xi2 plus so on up to plus xin equals to, sorry, not equals to, we are not written the value of I. Okay, so this equation has to be repeated for every I. So for I equals to 1, this equation becomes x11 plus x12 plus and so on up to plus x1n is equals to 1. Okay, so what this means is that I can write the equations for I equal to 2 and so on, but only one equation is sufficient to make the point. So uh, let's consider this equation, and in this equation again x12 is 1 because we want the summation of all the terms on the left hand side to be 1, which means only one of the term can be uh, 1. Every other term should be 0 because we already defined xij as a binary variable. That means the value of x must be 1 or 0. So if x12 is 1, every other x in this equation must be 0. And what this means is that I can travel to exactly one city from city 1. Okay, so here I am traveling to city 2 from city 1. I cannot travel to any other city from city 1. This is the meaning of this equation. Similarly, in the next equation for I equals to 2, let's say x2 1 plus and so on up to x to n, and somewhere here might be, let's say, x2 4. So in the second equation, if x2 4 is 1 and every other term is 0, which means that from city 2 the salesperson is going only to city 4 and not any other city. So this is the meaning of this constraint. Okay, so I hope that you have understood the uh, meaning of those two constraints. So anyway, let me clean this up. Okay, so here is an example of 5-city problem, the same example that we saw on the previous slide. And this picture shows a network, which means that every city is connected to every other city in the network. Okay, so this circle represents a city, or it is also known as a node. Okay. So all the nodes are connected to each other, or every node is connected to every other node in this network. Now, a traveling salesman problem can have two categories of solution, which are tour or a subtour. So here is is an example of tour solution where the salesman uh, visits every city in the tour. Okay, and the same tour consisting of 5 cities can be completed by doing two subtours. So the salesman starts from city 2, goes to city 3, come back to city 2. Then the salesman comes to city 1, starts the tour, goes to 5, from 5 goes to 4, from 4 to 1. Okay, so the tour is completed. So we are not looking for sub-tour solutions because this is not what we want. We are looking for tour solutions where the salesman covers all the cities in a tour in one shot. Okay, so the cost involved in sub-tour solution is obviously higher than the cost involved with tour solution. We're going to model traveling salesman problem as an assignment problem, and hence we are going to use the same tabular representation that we used in assignment problem. Okay. The objective function, the constraints, and the variable xij, which is a binary variable that can have only two possible values, 0 and 1, is same as that of the assignment problem. And if you look at the tabular representation, is same as that of assignment problem. On this axis we are from city, and on the horizontal axis we have to city. So for example, if the salesperson travels from city 2 to city 2, then the cost incurred is C2. Similarly, if the salesperson travels from city 3 to city 1, then the cost incurred is C31. Okay. but we know that our assumption is, or our requirement is that the salesperson should not travel to a city from the same city, and that's why the diagonal of this table has infinity. Okay, so the diagonal of the table represents traveling to a city from the same city, and that's why we assign a huge cost to this journey so that the model will never assign these values or these coefficients xij to 1. Okay, so we don't want this one, we never want this one, so that's why we assign a huge penalty here. Okay, so this is the meaning, and let's reduce this to a example of 5 cities. So n is equals to 5 for this particular slide. As you can see that the last city is given number 5. Let us solve an example. So a salesperson wants to complete a tour consisting of 4 different cities, city 1, 2, 3, and 4, and the values required for completing a journey from a particular city to other city are given in this table. So for example, if the salesperson travels from city 1 to city 3, then this is the value of C1380. So if the salesperson travels to city 3 from city 1, then X13 becomes 1, and then this 80 comes into the equation of objective function. Okay, otherwise it doesn't appear, because then xij becomes 0 if the salesperson does not travel to city 3 from city 1, then 0 will be assigned because x13 will be 0. Okay. So this is the meaning of the coefficients in the cells of the table. Okay. And to solve this problem, we are going to use the same Hungarian approach that we used in assignment problem. So let us do that. The first step is to row reduce the matrix or row reduce the table, and then to column reduce. So row reduction will ensure that every row contains 0, and column reduction will ensure that every column contains a 0. Okay. So this is the row reduction. You can just pause the video here and you can do the calculations. To do the row reduction, what you have to do is consider a particular row, find out the minimum value cell, and then subtract that value from every other cell in that row. Okay, so for example, if we consider row 1, and then we find out the minimum entry in row 1, which is 30, and we subtract 30 from every cell in this row. And if you look at the row 1 here, 30 minus 30 is 0, 80 minus 30 is 50, and 50 minus 30 is 20. So that's how we have obtained the first row here. Similarly, you can compute for row 2, 3, and 4 by pausing the video. So after row reduction, you can observe that every row contains at least one 0. Okay. Now, if you look at the column 3 does not contain a single 0 entry. So let us do column reduction. Okay. So this is the table after column reduction is done. You can again pause the video and do the calculations yourself. We are going to adopt the same technique here. We find out the minimum entry in a particular column and subtract that entry from all the other entries. Sorry, from all the entries, not other entries. So for example, if you consider column 3, then the minimum entry is 50, and we subtract 50 from every entry in column 3. So 50 minus 50 is 0, 110 minus 50 is 60, and 60 minus 50 is 10. And that's how we obtain the column 3. Then, according to Hungarian algorithm, we have obtained a solution only if we can draw a lines, or we can cross out all the zeros, and then the number of lines required for crossing all the zeros equals to the number of cities, then we have got a solution. Okay, so that is the Hungarian algorithm. So let me cross the zero. So that is one line, then those two zeros, and finally that zero in cell 4 1. Okay, so you can see that I'm able to cross all the zeros by using only three lines. So number of lines required for crossing all zeros is 3 here. But the number of cities is 4. So 4 is greater than 3. That means we cannot complete the assignment. Okay. And we continue to do so until we require 4 lines to cross all the zeros. Okay. So let us continue this. Okay, here is the picture from the previous slide, the same picture. I am putting it here for reference. And you can see that as only 3 lines were required for crossing all the zeros, we need to produce more zeros. And according to Hungarian algorithm, now we consider all the uncrossed out entries, which are those 6 entries. We subtract the least entry from all the entries. Okay, so we subtract 10. 10 is the least entry. So we subtract 10 from all the other entries. So this becomes 0. 60 minus 10 becomes 50. 20 minus 10 is 10. 30 minus 10 is 20. And the entries at the junction of the two lines are incremented by the same amount. So 20 plus 10 is 30. Okay. So this is the next table. Okay. The same table that I have rewritten over here. Again, we cross the zeros. So let's see how many lines are required. Those two zeros, those two zeros, and those two zeros. So again, the number of lines required for all the zeros is 3, which is less than the number of cities 4. And hence, we cannot complete the assignment. So again, we use the Hungarian algorithm and we look at the uncrossed entries and we subtract the least entry from all the entries. So the least entry here again is 10. So 10 minus 10 is 0, 10 minus 10 is 0, 20 minus 10 is 10, 50 minus 10 is 40, and the entries are junction are incremented by 10. So 30 plus 10 is 40. Okay. So this is the result that we obtained on previous slide, and let us try crossing out all the zeros. So this first line, then second line is required, one more line is required, and one more line is required. So now we require 4 lines to cross out all the zeros, and that means we can now complete the assignment. So let us complete the assignment. We will start from the row containing only one zero entry, which is row 3, and we will assign x3 4 to be 1. That means that salesman should travel from city 3 to city 4, and no further assignments are possible in column 4. That means as the city 4 is approached from city 3, it cannot be approached from any other city. Similarly, if the salesman is starting journey from city 3 to 4, he cannot travel to any other city from city 3. That's why we cross out the row. Okay. Then again, we look for the row containing only one zero entry, which is row 2 this time. And we make an assignment here by drawing the square box around the 0, or which means that x21 is 1. That means that salesperson should travel from city 2 to city 1, and then further assignments are not possible in row 2 and column 1. Then we again look for the row containing single zero entry, but I think now we don't have any row left containing a single zero entry. So now we can arbitrarily uh, break the ties. So let's say that I assign x13 to be 1. So that means the salesperson should travel to city 3 from city 1, and hence no further assignments are possible in column 3 and row 1. And now we are left with this single solution, which means that the salesperson to travel to city 2 from city 4, and no further assignments are possible here. So this is the solution. So let me write the sequence of the cities traveled as a tour. So starting from here, or maybe if we start our tour from city 1, we can start the tour from any city, but if we start the tour from city 1, let me cross out those arrows. Okay, so let's start the tour from city 1. Then from city 1, the salesperson should go to city 3, hence 1, 2, 3. Then once the salesperson reaches city 3, then he should go to city 4. Once the salesperson reaches city 4, he should go to city 2. Once the salesperson reaches city 2, he should go back to city 1 and complete the tour. Okay, so this is how we use Hungarian algorithm to solve the traveling salesman problem. So hopefully this video has given you an insight into how to solve the traveling salesman problem. I will soon add a few assignment problems so that you can practice with them.